You know that feeling, right? A website crashes the exact moment you need it the most. Well, today we're going to pull back the curtain on the powerful architecture that stops that from happening. We're talking about the resilient asynchronous pipeline. So let's break it all down.
Okay, let's start with a problem we've all experienced firsthand. You're trying to buy tickets to that huge concert, or maybe you're trying to snag some limited edition sneakers the second they drop, and boom, the site just hangs. That feeling of frustration? That's a classic sign of a system that just can't handle a sudden tidal wave of traffic. So, what's really going on under the hood? Well, it's a problem of sheer volume. When you have tens or even hundreds of thousands of people all trying to do the same thing at the exact same time, a traditional system tries to deal with every single request immediately. And, you guessed it gets completely overwhelmed. Things slow to a crawl, and eventually the whole thing can just give up and crash. This really gets to the heart of the matter. On the left, you've got synchronous processing. Think of it like a single file line at a coffee shop. You place your order, and then you just stand there, waiting for your drink, before the next person can even start their order. It's simple, sure, but man, is it slow. Now, on the right, we have asynchronous. This is a whole different ballgame. You place your order, you get a number, and you can step aside. The system can take a whole bunch of orders at once, keeping that line moving smoothly. So, how do we actually build a system that works like that super efficient coffee shop? The answer lies in a really cool concept called an event-driven architecture. Basically, instead of waiting around for direct instructions, the system just reacts to events as they happen. And this analogy right here is the key to everything. See, in a normal system, the part that takes your order has to directly call the inventory part, which then calls the shipping part. It's like a conference call. If any one of them is busy, the whole call is on hold. But in an event-driven system, the order taker just pins the new order to a central message board. The other departments, they can just walk up to the board and grab the next job whenever they're free. This is what we call decoupling, and it is an absolute game changer. Okay, so let's get into the weeds a bit. We're going to follow a single order placed event and see exactly how it travels through this modern asynchronous pipeline. It's pretty slick. So the moment you click that buy button, your order instantly becomes an event. Its very first stop is a service like Amazon's SNS. The best way to think about this is as the system's town crier. It receives that brand new event and basically shouts, "Hear ye, a new order has been placed," to anyone and everyone who needs to know about it. So who's actually listening to this town crier? Well, that's where our next piece of the puzzle comes in. SQS. You can think of these as digital waiting rooms. The announcements from the town crier get caught and placed neatly into these queues. So if 1,000 orders come in at once, they don't cause a panic. They just form an orderly line, waiting patiently. This queue, right here, that's the magic buffer that prevents the whole system from getting swamped. Okay, so we've got messages piling up in our waiting rooms. Who actually processes them? Meet our specialist workers, AWS Lambda functions. These things are awesome. They're just tiny, super efficient pieces of code that do one specific job and one job only. You might have one Lambda that's in charge of updating the inventory, another one's job is just sending confirmation emails. They literally wake up when a message appears in their queue, they do their job, and then they go right back to sleep. They're completely independent. All right, let's put it all together and see the whole flow. An order event gets published to our town crier, SNS. That message gets fanned out to multiple waiting rooms, or SQS queues. Then, our independent, specialized Lambda workers pick up those messages and process them, each at their own pace. And you know what the best part is? The user, the person who placed the order, they got an instant thank you message. They have absolutely no idea about all this incredible work that just kicked off in the background. Now, this all sounds amazing when everything's running perfectly, but let's be real. In the real world, things break. What happens if, for just a moment, the payment processor service goes down? Does the system just lose the order? No way, absolutely not. This is where the resilience of the system really starts to shine. See, this architecture is built expecting things to fail. If a worker tries to process a message and it fails, maybe a database was busy for a second, it doesn't just give up. It's configured to automatically try again, in this case up to 3 times, usually with a short delay. Most of those temporary glitches just fix themselves this way, with zero human intervention. But what if it fails all 3 retries? Maybe there's a real legitimate issue with that one specific order. Even then, the message isn't just lost in the void. It gets moved to a special queue called a dead letter queue, or DL queue. Think of this as an investigation desk. The message is safely set aside so engineers can look at it later and figure out what went wrong, all without blocking the main pipeline, which is still humming along, processing all the other healthy orders.
So, we've walked through the how, but what's the big payoff for all this complexity? The why is where this architecture goes from being a cool idea to an absolute necessity for modern applications. It really boils down to three massive advantages. First up, scalability. This is huge. If you suddenly need to process more payments, you can just scale up the payment workers without touching anything else. Second, resilience. Like we just saw, the system handles temporary failures on its own. It basically heals itself. And third, decoupling. The team working on inventory doesn't need to schedule meetings with the team working on shipping. They're independent, which makes development so much faster and safer. All right, so let's just quickly recap the core strategy here. First, you decouple your services so they're not all tangled up together. Second, you use queues as that critical buffer to absorb those massive traffic spikes. Third, you have to plan for failure from day one with automatic retries and dead letter queues. And there are a couple of other crucial points here. You have to make sure your system doesn't accidentally process the same order twice, and of course, you have to monitor everything to make sure the whole pipeline is healthy. And that really leaves us with a final question to think about. It's pretty easy to build a system that works perfectly on a sunny day when everything is going right. But a truly great architecture isn't just built for success. It's built for resilience. It's designed from the ground up for those moments when things will, inevitably, go wrong. And that is the difference between a site that crashes under pressure and one that scales beautifully. Thanks for joining this Explain.